All right, so we'll start with a overview of this new field of flexible electronics, and today and maybe next lecture we'll just skim over why people are interested in this particular field. Okay. Now, if we draw, in order to appreciate flexible electronics, you have to understand, if I just draw this world of electronics, flexible electronics is a very small part of it, a very small part of it. And in order to understand, and this is, in terms of, let's say if you start talking about in terms of revenue, number of industries acting in this particular field, number of researchers who are working in this particular field, it would be really very small field. It's an emerging field, okay? And to understand why people are interested in this particular field, you have to understand at least the rest, this world of electronics. This world of electronics that is all around you, how did it develop? How did it start? How did it develop? And in particular, what are its limitations? Its strengths are obvious, right? All the products, I mean, the modern world is dominated by electronics, and all of you are carrying lots of electronics in your pockets. So its strengths are obvious, but what are its limitations? Okay, so that's what we will try and focus on. And you would see that the world of, the field of flexible electronics is trying to address some of those limitations and saying that electronics can be done in a different way, which overcomes some of the limitations of traditional electronics here. All right, so we'll start with the world of electronics, how it started, right? So very broad view of what does that world look like, okay? Well, whenever at least I'm asked what is the reason for the modern world being dominated by electronics, there are so many other fields that are there, but it's heavily dominated by electronics. And in very simple terms, the answer that I would like to give is based on some obvious statements, self-evident statements. The first one is self-evident, which no one would disagree, that every action requires energy. No matter what you want to do will require energy in some form, right? So that's a self-evident statement. The second one is also, I think most people would agree, electricity is one of the most useful forms of energy. Easy to generate, easy to transport, easy to convert into other forms of energy. If somebody were to tell you, carry light from one place to the other, or carry heat from one place to the other, thousands of kilometers, you can't do that. Right? Or an audio signal, speech signal. Somebody says speech signal as it is, take a speech signal from here and carry it 100 kilometers from here. It won't go. Right? So that's what I mean by easy to transport, easy to generate, easy to convert. These are things that you're well familiar with. This also would not be a controversial statement, that electricity is one of the most useful forms of energy. And the reason now why electronics dominates, if you go by these three, the other one is it can be precisely controlled. There is no other form of energy that I would like to claim which can be as precisely controlled as electricity. If you take heat or mechanical energy or whatever other forms of energy, you cannot control it to the same extent, like electricity. So now if you accept these three statements, to do anything requires energy. Fine. Electricity is one of the most useful forms of energy, and it can be precisely controlled. Precisely controlled means you can make it do whatever you want. If you can control it, well, you can make it, whatever you're thinking, you could, as we said, every action requires energy. And so whatever action, whatever you're trying to do it through electricity. Why? Because you can precisely control it. right? So these three statements by themselves tell you the source of why electricity is dominating our lives, why electronics is dominating. Electronics is what allows you to precisely control it. So why electronics is dominating our lives? Because of these three statements that you're looking at here. So in that sense, when I'm saying every action requires energy, then it basically becomes imagination is one of your biggest limitations in terms of what you can make electronics do. So in principle, all this is fine, right? I mean, if you agree with these three statements, then it says, well, every action, so you have to think of what do you want to do? Whatever you want to do, well, you could use electricity to do it. By some way or the other, I mean, take your driverless cars, right? We are all talking about autonomous driving. Well, you are interested in autonomous driving. How do you get to autonomous driving? What are they trying to do? They're trying to do it through electricity. By using sensors, actuators, all the processes, everything that is involved is all based on electronics. So whatever is your objective, whatever you're trying to do, try to do it. You will require energy to do it. Try to do it through electricity. Why? Because you can control it. You can control it far more than anything else that is there here. Well, so all this is fine. In practice, to do anything interesting, let's say you have an electrical element or an electronic element. To do something interesting, you need to integrate lots of them, right? I mean, from your natural system, you know that a single cell, for example, is useful. There are organisms which are single cell. But to really do complicated things like the way human beings do, well, you need to integrate lots of cells. You need huge billions of cells have to be integrated in order to achieve something which is complex. Otherwise, a single cell will only do something which is very simple, right? In the same way, if I have an electronic element or an electrical element, the single element will do something very simple. But if you integrate lots of them, lots and lots of them, then you can do very interesting things with it, right? So if we are saying that imagination is the main limitation of electronics, you want to do nice things with electronics, well, then you'll have to integrate. You have to achieve large scale of integration. You have to integrate lots and lots of electrical elements. Whatever those electrical elements are, we'll see in a minute. You have to integrate lots of them. Then only you'll achieve a functionality which is interesting. Otherwise, a single element, 2, 3 elements, 4, 5 elements by itself would be interesting, but will not do much for you. Okay? So what is extremely important in electronics, if you want to understand electronics, where did it start and the trajectory that electronics has taken, and the place where electronics is going. If you want to understand it, the key word is scale of integration. How large, how many circuit elements can you integrate in an efficient manner in order to do useful things? So the integration, the scale of integration is one of the dominant themes in electronics. And so let's look at it. When did electronics start? Well, some people may say diodes, but I would rather say triode. Diode is useful, but just with the diode you can't do much. But with the triode, so electronics started with this particular invention here, 1906 triode here, vacuum tube electronics that was there. And what was interesting, I'll not go into the details of about a triode, but what was interesting about a triode, you can read more about it. It's a 3-electrode element, just like all of you are familiar with transistor. So it's a 3-electrode element. There's an anode and a cathode. So you apply a voltage and current flows between anode and cathode. And there's a third terminal called grid. So you apply a voltage to the grid and you can control the current flowing between anode and cathode. Okay, so that's in essence what a triode is. So it's a vacuum tube and with 3 electrodes, and you apply a voltage to the grid and it controls current flowing between anode and cathode. Right. Now, what happens is current is flowing between anode and cathode, and you're controlling it through a third terminal, which is grid. So this was one of the first devices which exhibited what we call as transconductors, because current is flowing between a 2 separate pair of terminals, anode and cathode, but you're controlling it by another terminal, which is the grid. So it exhibited a property called transconductance, a very interesting property. But what was interesting about not just that it exhibits transconductance, the transconductance is much higher than the normal conductance. That is what is very interesting about this particular device which caused the revolution. Normally, if you have two pairs of terminals, cathode and anode, right? You apply a voltage, current would flow, let's say. If you change the voltage, the current would change. And the change in current with voltage, what do we call it? Conductance, normal conductance, and let's say we call it output conductance. Now, it would be very strange for you to believe that, fine, I have anode and cathode, current is flowing. I change the voltage across it. The current changes very little. But then there is another terminal located somewhere else. If I change the voltage there, the current changes a lot. Right? So transconductance is much higher than the normal conductance. That was a very, very strange characteristics of this particular tube here. Transconductance was much higher than the output conductance. And we can easily show through this that transconductance is much higher than output conductance. We can easily show that, well, this element was capable of amplification. That you apply a small signal and then you could get a higher signal here. A weak signal could be translated into a higher power signal here. So this was capable of, tube was capable of amplification. And sometimes I like to call amplification is the heartbeat of electronics. If amplification were to stop for whatever reason, let's say if amplification were to stop, all your electronics will ground to a halt. It's like the heartbeat. You stop amplification, everything stops, everything falls dead. It is central to electronics, amplification. And this was the device, the triode, which launched amplification. Before that, you could not amplify an electrical signal. Okay, you could attenuate it, you could put resistors, capacitors, inductors, all those things were there. You could even take rectify it, but you could not amplify it. Right? So this was the device which enabled amplification. And as I said, amplification is at the heart of electronics. Whether you want to do analog circuits, you want to build any digital gate, you want to build NOT gate, NAND gate, any of those things, amplification is central to it. Right? So this basically launched electronics. I'll not go into the details of it. 1906, right? 1906, and then one of the heights of vacuum tube-based electronics was this early computer that you see in 1946. This was like the pinnacle of vacuum tube-based electronics. In 1946, you see this early computer called electronic numerical integrator and computer here. As I said, to do anything interesting, you have to integrate lots of these elements. So let's see the scale of integration of this particular early computer. All right, so the scale of integration was, you can see it here, the ENIAC contained 17,468 vacuum tubes. Fairly reasonable number of vacuum tubes, along with 70,000 resistors, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and 5 million soldered joints. 5 million, you'll have to go and somebody soldered it 5 million joints. And it occupied an entire room that you see here. This whole room, big room, was this early computer, weighed 30 tons, consumed 160 kilowatts of power that you see here, and its power was, I won't even dare to compare it with a mobile, but its power was maybe like your calculator, early calculators that were there. Its power was at that particular level. In terms of computational power, that's what it could do, okay? And it was not very reliable. You can see here, 19,000 vacuum tubes had to be replaced in 1 year. Imagine you have to take your whatever electronics you're carrying. It's like 50 tubes a day. It's like 50 elements burn up a day and you have to carry and get it repaired. Right? So that was the state of electronics. So in principle, the triode was a fascinating device in terms of its property, in terms of the principle that it could amplify. And with the amplification, they could make radios, they could have transatlantic communication, all those things happen. A telephone, long distance telephone became possible. Because with amplification, if you call, after a while, you can have a repeater which amplifies the signal again, and then you send it again, and long distance communication using telephone, radio, all that became possible. Not only that, digital computers were made. So you could do all of these things in principle, but you can see how hard it was, how difficult it was. So much space, so much power, so unreliable, right? So you could, I mean, it was hard. So in principle, you could do a lot of interesting things. In practice, it was hard. Okay. So what I would say is the seed of electronic revolution, which you see all around, was there in triode itself, but it was difficult to harness it. You couldn't integrate lots of them in a simple manner and do interesting things with the diode, right? And 1946 is what I've shown here. This was in 1946. It's like the height of vacuum tube-based electronics. So we're talking about almost 40 years. So when electronics started, 40 years of electronics was vacuum tube based. 1946 or so. Why 46? I'm putting it here because all of you know the transistor came. Now people realize that you could do in principle so many interesting things are possible with electronics, but vacuum tube is not the right way to do it. You have to look for a new element. And so research was on at various places to look for an alternative, and a breakthrough occurred in late 1947. I put it here as 1948. Breakthrough occurred, which was the invention of the transistor. More like a discovery of the transistor. I'll forward some papers you can read. How you should all read. All electronics engineers should read the history. How was the transistor actually invented? What really happened? So 1948. So you see 40 years of vacuum tube electronics, and then there's a sharp turn. The electronics became transistor based. So a transistor was invented, and bipolar junction transistors were the first transistor was more of point contact, and then it became a junction transistor. And so a new era of transistor based electronics started. And what I've shown here is what basically occupied an entire room now could fit. This is a early calculator by Sharp, 1964, early calculator. And these are all based on bipolar transistors. You can see here 530 germanium transistors and 2,300 diodes and all that. So earlier, what occupied an entire table could fit onto a tabletop. That was the, in terms of space, that was the saving. An entire room now could be put onto a tabletop. Something that weighed tons is now 25 kgs. Something that consumed kilowatts of power is only 90 watts of power. So you could see the tremendous savings in power, in space, and it was very reliable. This was highly reliable. The calculator once made, you don't have to go and replace transistors every day, or transistors are much more reliable as compared to the vacuum tubes here. So tremendous improvement, and as a result, one could integrate now a lot more transistors. So this is a rather simple example of only 530 germanium transistors, but you could integrate a lot more transistors and do complex things with it. So transistor now enabled greater scale of integration. With vacuum tube, you were limited. Its size became large and power became large and all that. With the transistor, you could now integrate a lot more elements. But note that transistor, you could do a lot more. Transistor was very small, and you could do integrate lots of them. But even now, it's not very easy. Realize this. Look at this one here: 530 germanium transistors and 2,300 diodes. It's not a very large circuit in terms of integration. But look at the power: 90 watts of power and 25 kgs. So all of you think that, well, transistor is small and therefore I can integrate lots of them, but it's not so easy. Even with the transistor, it's not so easy. What occupied a room occupied a tabletop. But then this is only 530 germanium transistors. Suppose I want to build a circuit, do some more interesting things, and I want to build a circuit with, say, 100,000 transistors. How large would it get? Well, integration level was much better, but was still limited. And actually, electronics had to wait for a new invention. It was not the transistor, in maths we say necessary and sufficient condition. So if somebody to ask you what are the necessary and sufficient conditions for electronics to have reached where it has reached now, transistor was the necessary condition, let's say, and the sufficient condition was the next invention, which was a new method of making circuits, which is the invention of the IC. New this thing here, and this is extremely important to understand. Many times we give a lot of importance to transistor. We don't give as much importance to the IC. In fact, you would have entire courses talking about transistors, but you don't have you don't go through any course about how are these things made, how are ICs actually made. We devote 1 or 2 lectures, if at all, in terms of how these things are actually made. But without this IC, electronics wouldn't have been, none of the things that are happening now and you're carrying in your pockets and all that, none of these things would have been possible without the IC. And it took, while the transistor was invented in 48, and I think a Nobel Prize was given in 1955 or 56, immediately the importance of transistor was realized. IC got a Nobel Prize in 2000. It got a Nobel Prize. The importance of IC was realized much later, what it has achieved, right? So what is this IC that I'm talking about? Note that we are talking about, by the way, the word IC is in some sense, gives the wrong impression. Integrated circuit. All circuits are integrated circuits. You're integrating elements. You're taking, when you build something on your breadboard, you're taking 4 or 5 transistors, resistors, capacitors, and you're integrating them. So in some sense, everything is an integrated circuit. You are integrating elements. Any circuit is an integration of elements on some substrate. Breadboard, PCB, or whatever. In some sense, everything is integrated. Important word here is monolithic. Monolithic IC. And this is one of the inventors. There were 2 inventors, Jack Kilby from Texas Instruments and Robert Noyce from Fairchild. And 2 inventors are there. And what you see here, this is a patent filed by Jack Kilby from Texas Instruments, the first patent on an IC. And these are his drawings of what an IC is. And it's important what he writes here in this. It is to be noted that all components of the circuits are integrated into the body of the semiconductor material itself. Okay? All components circuit are integrated into the body of the semiconductor. Now, what does this really mean, monolithic IC here? Okay, so what happened was, before we go into what happened was 1958, as I said, 1948 to 1958 is where the IC is invented, right? So from 1948 to 1958, you have an era of what we call as bipolar transistor-based discrete circuits. Discrete means discrete transistors and you interconnect them on a PCB. So that was the era here. From 1958, switched to a IC-based circuits. IC-based, electronics became IC-based, not on the basis of discrete transistors, but it became IC-based. And this is from 1958 onwards here. Now, it's very important to realize, as I said, if transistor was necessary, monolithic IC is the sufficient condition. It's one of the key inventions. And to understand flexible electronics, you need to understand the concept of monolithic circuit. Okay? So, this is a transistor that you are all familiar with. Right? You have all seen in the lab the transistor that you see here, right? So this is a transistor which is inside a package, right? With 3 leads, emitter, base, and collector. If you could open it, this particular transistor, what you would find inside is a tiny piece of silicon. A tiny piece of silicon, and is inside a metallic case with some leads that, with these pins that are coming out. If you look at this tiny piece of silicon that you see here, maybe in the center is your emitter, this is the base, this is the collector. That's your bipolar transistor. Now, this is the bipolar transistor that you see here, this part here. This is your bipolar transistor, emitter, base, and collector. This bipolar transistor can be made very, very small. Even in, let's say, early days, you could easily make it, say, 50 micron by 50 micron, let's say. You could, and it's not that hard. You could make it 10 micron by 10 micron. You could really make it very small. The transistor, emitter, base, and collector, you could make it very small. But then, this is where then it becomes important. So the transistor is very small, right? In microns. Now, how do you connect one transistor to a resistor? You have a transistor, which is extremely small, and you have a resistor. Resistor, all of you have seen. The resistor is there. You want to connect a transistor to the resistor. How do you connect them? How? This small transistor, what would you do? Let's say you are the one who's making the circuit, right? The transistor is there on a small piece of silicon. It's a tiny, extremely tiny piece of silicon, few microns by few microns, 50 micron by 50 micron, very tiny piece of silicon. 50 micron by 50 micron, you would have very, it would be, if we were to give you, you'll have a hard time seeing it, right? And now I'm asking you to connect that 50 micron by 50 micron transistor to a resistor. A resistor size would be what? A few millimeters or centimeter maybe. Connect them. How would you connect? Well, to make an amplifier, let's say you have to connect the collector of the transistor to a resistor and base also to a resistor. Make an amplifier. How will you connect them?
Create large contacts then in order to...
Right, so this is the transistor. And I want to connect a resistor. How do I connect it? What is your method of making circuit? Forget about IC for a moment. What is the method of making circuit? Before IC, what was the method of making circuits? Huh? Taking a component in hand, or if you don't want to have a hand, maybe a machine will hold it. A machine as a surrogate of a hand. So you have to hold the component transistor in your hand, and you have to hold the resistor, and you have to put it on a substrate and solder it, right? So you'll have to pick the transistor up, right? Wherever the transistor is lying in your plate, you'll have to pick it up, and you have to place it on your substrate. So you have to pick and place, and then you will have to solder it. How do you pick a 50 micron cross 50 micron transistor and place it on a substrate? How do you do it?
We need to build a large enclosure for it.
So you're saying I can't even see that 50 micron transistor. I'm making things very small. I could make in principle very small, but I can't even see. I can't handle it. I can't pick it and place it. So what did they have to do? As he rightly said, the transistor is very small, but I have to make it large. I have to artificially make it large. I have to make it large, so I have to put it in a package, inside a package. And inside a package, how do I put it? Well, we create all these pads that you see here, metal pads. So we take our transistor surrounded by a large metal pad for emitter, base, and capacitor. So these pads are there, and now these pads that you see, these leads are there. These leads are eventually connected to these leads here. So there's a lead coming here, and there's a lead coming here, and there would be a lead coming here. Wires connecting and connecting. So you artificially make it, or what? You make it of a size of like a centimeter, a 1 centimeter square, or whatever, something of that sort. You have to make it so that you can easily pick and place. Why do you have to do that? It's because of the nature of manufacturing. The manufacturing method is what? Pick and place. The manufacturing method is pick and place. So your components have already been made, and you pick a component and you place it, and then you interconnect, solder it, and put wires and things like that here. So you're artificially making it large. So once your transistor becomes a centimeter, now you can calculate, do some calculation and say if you want to integrate 10,000 components, how large will it become? The size of, 1 centimeter by 1 centimeter, the size will become large. If you have to make 100,000 components, the size will become even large. So the size of your circuit becomes larger and larger. Suppose there's a transistor here, and there's a transistor here. The size of the circuit is becoming in meters. So this transistor would be connected by a length of wire which is 1 meter. When you have a 1 meter long wire, it has a lot of capacitance in it. So once you have a lot of capacitances have to be charged and discharged, so the whole thing gets slow. So the whole thing becomes large, slow, you get into all these problems. So very early on, that's what, for example, Jack Kilby and others who were making circuits with transistors at that time realized that yes, transistor is very nice. But then if I want to build something interesting with it, I'll have to integrate a lot of transistors, and then we get into this problem that my circuit is again becoming very large. Circuit is again becoming very large, and it's causing a problem. So this is how, for example, this is like an op-amp, operational amplifier with a couple of transistors that you see, and this is how people would make the op-amp. By each one of them is a transistor, and you have resistors and capacitors and all that on a large PCB, right? That's how the circuits were manufactured, right? So this is what we call as, the word that I'm using is discrete. Discrete way of manufacturing circuits, right? Discrete. What do we mean by discrete? Components have already been made. A resistor has already been made. A capacitor has already been made by whatever method. A transistor has already been made. Now you take those transistors, they're all available as discrete entities. Now you pick up those transistors and elements and you integrate them on a breadboard or a PCB. Breadboard is just a prototyping, a PCB, a printed circuit board. So you integrate it there. Right? So that's the method of manufacturing, which we call as a discrete circuit. It's a circuit, but it's a discrete circuit. And discrete circuits, you have a problem. They will again become large, and they will have problems of size and power and speed, and all those problems will come. Okay? But then people realize at that, those who looked at it, that unlike vacuum tubes, this transistor, they realize, why can't I, suppose I have to interconnect two transistors. Why do I have to make one transistor separately, another transistor separately, and then interconnect them? They realize, why can't I make one transistor and next to it on the same silicon make another transistor, right? And then interconnect them on silicon itself. Deposit a metal on silicon itself and interconnect them. So they realize, for example, if you just think of a two transistor circuit, two transistors are there, collector of one is connected to the base of another. Why do I have to make two transistors separately, pick them up and place it and connect them? Why can't I make both the transistors on the same piece of silicon and interconnect them? So that seemed logical. It seemed obvious. Then the next question they asked was, all circuits are not made of transistors. I require resistors also. So they said, can we make resistors on silicon? They said, yes, you can make resistors on silicon. Because semiconductor is what? Semiconductor is, has a reasonable resistance in it. So they realized, well, if I require a resistor, why don't I use silicon as a resistor itself? So they realized, well, what does a circuit really require? It requires transistors now, it requires resistors. They realized, well, we can make resistors also. Then they thought, well, at some places I require capacitors. Can I make capacitors? Well, they saw, well, we could make capacitors. For example, we could have a metal, and we could have a dielectric silicon dioxide on top and put another metal on top. This something is on silicon I can do. Metal, silicon dioxide, metal, it becomes a capacitor. Or I could use a reverse bias PN junction which acts as a capacitor. So they realized, well, capacitors also we can do. So they said, why can't we just then make all the things on the silicon itself and interconnect them on silicon itself? And then where are we going? We are going towards what we call as a monolithic IC. Mono means single. Monolithos, single stone. So on a single piece of semiconductor, we are going to make all the transistors that I require, all the resistors that I require, all the capacitors that I require, and interconnect them also. Then the whole thing becomes very this thing here. And that's what you see. And early, you guys are all familiar with the 741 op-amp. It has all these 25 transistors, resistors, capacitor. Capacitor is only one. So everything is made on the same piece of silicon here. All the transistors, all the resistors, all the capacitors are all made. And they're all interconnected. They're all interconnected here. And once you've made the whole thing, now you go ahead and package it. Put it in a package. Now you can use an op-amp as a discrete entity. But now this 25 transistor circuit, it only, you can see here, only measures a centimeter. So it allowed a 25, with all these, the whole component count maybe, 50, 60 component count, but the whole thing could be fitted into the size of a single, same size as a single transistor package. almost here. So this now was a new way of making circuits now, making things on the substrate itself. All the transistors, all the capacitors, all the resistors, everything is made and then interconnected. And this is what we call as monolithic. And with this monolithic circuit came the advantage, lots of other advantages. You are saving all the package costs. Imagine if you have a 25 transistor circuit. Now, earlier you would require 25 packages. You don't require 25 packages, you require only one package now. So there are a lot of savings in terms of cost, and all the transistors are made simultaneously, all the interconnects are made simultaneously. See, there's a saving of cost, reliability. It's a very compact circuit that you have. And so integrated circuit, a monolithic integrated circuit brought all the huge number of advantages and solved one of the key problems of integration. I could now, in principle, because the transistor, note that the transistor is very small. So I could, in principle, connect lots of transistors and my circuit still stays manageable. Then the next point that they saw was that the transistor, fine, you're making a 50 micron cross 50 micron transistor. Transistor has, if you reduce the size of the transistor to 20 cross 20, 10 cross 10, 2 cross 2, it would still work. Transistor characteristic doesn't depend on the size. And if you could shrink the size, I'm not going into the details, they saw that, well, you could shrink the size of the transistor also. And therefore, you could make more and more complex circuits without increasing the size of your IC that is there here. And this is, all of you know, early on, Gordon Moore, who started Intel, he looked at, he had these 4 data points that you see here of integrated circuit. 1961, he's making so he had these 4 data points of, once the integrated circuits were invented, this is the, the scale of integration of an integrated circuit at this year, then this year, and this year, and this year. And he saw, well, there's no inherent limitation in how large a circuit you can make. And he predicted that the complexity of the integrated circuit can increase exponentially, almost like doubling every 2 years or so here. And so he's saying, in principle, I don't see any limitation. And if the industry, if everybody together, they work, well, we can steadily decrease the transistor size, and we can increase the number of transistors, and we can make more and more complex circuits here. And he said circuits would continue to evolve exponentially here. As you can see, complexity would keep on increasing exponentially. This is what is called as the Moore's law here. So what happened was, this is where we are, right? 1958 is when the IC is invented. And you have an era of BGT ICs. Some of the ICs that you have used in, especially in ESE 201, those who are undergrads here, labs, TTL ICs and all that you see, they were all invented at that particular time. TTL counters and NAND gates and all those gates were all, they all belong to this particular era here of BGT ICs here. Lots of other interesting things happened around this particular time, 1958. One of them was 1959 MOS was invented. As you realize, first transistor was a bipolar. And why was a MOS invented? In fact, if you go back to the history, they were trying to make a MOS, a field effect transistor. In this group at Bell Labs, Bardeen, Shockley, and Brattain, they were all trying to make a field effect transistor. They failed to make a field effect transistor, and in the process discovered a bipolar transistor. Right? By accident, they discovered a bipolar transistor. And so it was bipolar. But then I'll not go into the details, the community that were looking at it realized that bipolar transistor is not very good from the point of view of integration. It's a vertical device, emitter you have to make, then base you have to make, collector you have to make. It's not a very good device from, if you want to integrate lots of transistors, it's not a very good device. On the other hand, this lateral field effect transistor, I'll come to in a minute, is a much better device. So even though bipolar transistor had been invented, people were looking for a better transistor. So they were still working on a better transistor than a bipolar, and finally they invented this in 1959 is what MOS was invented. And so what happened, it took some time for MOS, see, this is the invention of the MOS, it took some time for MOS to mature and become ready for commercialization. And this is one of the landmarks. This is 1971, Intel launches its first microprocessor, 4004. And it was a MOS-based microprocessor. And I would say from 1958 to 1971 is an era of bipolar ICs. After that, 1971 onwards, you have a MOS-based ICs. It's not that bipolar disappeared. Bipolar is still there, it's used. Bipolar ICs and transistors are there. But electronics was dominated by MOS. 1971 onwards. And there's been, as all of you know, has been a steady decrease in size of the transistors. Started off with some 10, 20 micron channel length transistors, became, you can see here, 2005, 90 nanometer. Right now we are around 4, 5 nanometer. You all read about it. So 2019, this is where we are. And, you know, with so many transistors, as I've been saying, the scale of integration has increased to such a large extent, 100 million transistors per millimeter square. Right? So you can imagine you can easily make a chip a few centimeters by few centimeters. And the transistor density is 100 million transistors per millimeter square. So you have so many transistors available, billions of transistors available, so you can do many interesting things. And one of the consequences of interesting things is that now, you know, we're talking about all this machine intelligence and all that that is there here. Where does flexible electronics fit into all this? Right? This is the traditional electronics that you see here. Right? So you can see all the important milestones. Triode here, bipolar transistor here, 58 invention of the IC, and then invention of the MOS also, 1959, and the era of CMOS electronics starting from 1970s. Okay? This is also a very important invention of the microprocessor. Okay? Invention of the microprocessor, and which started all this era here. So this is the electronics that is there. Where is this flexible electronics? Where does it fit into this here? Okay. Now, to bring a perspective on flexible electronics, we have to understand something else happened at this particular point here. When I'm saying MOS, in fact, if you go back in history and you look at the first, if you want to say who was the inventor of the transistor, the inventor of the transistor was this guy, Lilienfeld. As early as 1926, he patented a device which is a transistor. He described a device which is, about patents is interesting. You don't have to make it. To file a patent, you need to have an idea, and you can describe the idea, how it will work, and this, and it should seem feasible in principle, and you can file a patent. And so he filed a patent. He couldn't make it. He filed a patent of the transistor here in 1926. He could not make it, and after that also nobody could really make this particular device here. Now, what was the device? So if you want to know which is the first concept of a transistor, 1926, so let me explain what in simple forms, the kind of device that he was proposing. Remember what was there? Vacuum tube. Vacuum tube had what? A tube with anode, cathode, and a grid. And what does a grid do? Grid controls the current flowing between anode and cathode. So everybody knew the limitations of vacuum tube. So he is trying to think of what can replace a vacuum tube. What can be better than a vacuum tube? So this is the device that he came up with. He said, if I take glass, and I put 2 electrodes on top of it, fine, makes sense. One can deposit metal on top of glass. And then he says, well, inside the glass, if I can embed another electrode, okay, embed it here, and then put a material here, like a semiconductor, right? Semiconductor. And then if I apply an potential between these 2 electrodes, because it's a semiconductor, current would flow between them. Here. And then he said, this is the current that is flow. Then he said, well, if I apply a potential here, at this, by electrostatic action, he's forming a capacitor, if you can see here. This is a metal plate, in between there's a glass, and then the other one is also a semiconductor. It's like a conductor, right? So it's forming a capacitor. And so if I apply a voltage, so you can think of, let's say, this as, let's say, ground for a moment. And so if you apply a potential between this plate and this plate here, right, between these two plates here, this is like here. So what I can do is by applying this potential here, I can alter the charge here. Right? It's a capacitor. So any change in voltage delta V here, delta V should cause a delta Q equal to C delta V. There's a capacitance here between these two plates. That's what he was thinking. So I can change the charge. And once I change the charge, I can change the current. Right? So you could call it a gate here. So what I could do is delta VG. So what I can get is delta I by delta VG. And so I can get what we call as transconductance. A change in current. Current is flowing, let's say, if you want, you can call it like a source or drain, anode or cathode, whatever you can call. So current flowing between source and drain is being controlled by a gate voltage. It's just like a vacuum tube. Current is flowing between two electrodes and you're controlling it by a third. So instead of vacuum and all that, he conceived of this particular device here. Okay, if I deposit a metal here and a metal here, and then control it and deposit a semiconductor and control it with this, then it will behave in the same way as a vacuum tube. I will get transconductance and I will get amplification and all that. So this was the device that he patented. He was ahead of his time. He thought of it, but couldn't make it because there are a lot of challenges in making it. How do you put this electrode here? How do you get a reliable semiconductor? All these things that are challenging. So he couldn't make it. So this is what we call as because of electrostatic influence, we called it as a field effect transistor, right? Field effect transistor here. Why field effect? It's a transistor. Why are we calling transistor? Because you can control, it exhibits transconductance. You can control the current flowing between source and drain through the gate terminal. We're calling it a transistor. Field effect, why? Because of the electrostatic field. It's the electrostatic field, it's a capacitive action. I'm using it to control the current flowing between source and drain. So that's why the name field effect. And it's also called a thin film field effect transistor. Why thin film? Because note that we have glass here, which is a thick millimeters of glass that are there here. And what he's talking about, a thin film or thin layer of semiconductor being deposited here. Because through the gate, he wants to control the current flowing here. Now through the gate, you also want to remove all the charges from the semiconductor to turn the current to zero. If you want to make a switch, you will have to remove all the charges. So he's talking about a very thin film of semiconductor. So if it's a thin film of semiconductor, through electrostatic action, maybe you could remove all of them. So he's talking about a field effect transistor and talking about thin semiconductor film. So that's why we call it we call this device as a TFT, a thin film transistor. So the first transistor that was ever conceived, for which the first patent was filed, was a TFT. It was not a BJT, it was not a MOSFET, it was not a JFET, any of those transistors that you know of. It was a TFT, a thin film transistor, right? So this is what he's describing here, a TFT. This is what is just to contrast it, all of you know it, this is not a thin film transistor. Note that a MOSFET that you're familiar with is made on these silicon wafers. And on the silicon wafers, you see N plus and all those things that are there, SiO2 gate and all that is there. The thickness of these wafers are 400 microns. It's a crystal. The MOSFETs are made on single crystals of silicon here. So it's 300, 400 micron thick. And in contrast, the semiconductor here could be less than a micron thick. In fact, it could be only 100 nanometer thick. So we're talking about very, very thin films of a semiconductor deposited on glass. Note that deposited on a semiconductor like this, deposited on glass. In contrast, the whole thing is a transistor here, made on a crystalline silicon here. So it's both of them are based on field effect principle. This is also, note that we call it a MOSFET, right? We call it it's a field effect transistor. This is TFT. It's a field effect thin film transistor. It's also a field effect transistor. Both are field effect transistor, but there are very different ways of making it, right? And so at this particular time that you see here, 1969, right? 58. What you have, as I said, people were not very happy with bipolar transistors. They knew this alternative form of transistor existed, right? Alternative form of transistor existed. They knew that. And as you can see here, this is one of the persons, well-known persons in the field of thin film transistor. He said, he's making a statement. Some semiconductor workers realized that individual device performance was going to be less important. What is important is fabrication, simplicity, yield, and real estate occupied on the wafer. Thus, the search was on for a simpler, more easily manufacturable, and a more compact device than bipolar transistor. People were looking for something better than a bipolar. They knew that MOSFETs and all that field effect transistors could be better. They were simpler in nature. Instead of making a collector, vertical collector, and then base, and then, these are much simpler in terms of fabrication. And as a consequence of it, I said MOS transistors were invented in 1959. TFT, for the first time, TFT could be fabricated in 1959 also. So in this year, 1959, two field effect transistors were sort of in. I won't say TFT was invented because invention was already there in 1926, but TFTs were fabricated and they could show transistor action. Okay, and MOS transistor was also fabricated, 1959, and both field effect transistors were born in the same year, MOS transistor and TFT. Both were born here at this particular point of time. So now what was interesting was the community of people who were there, they had two transistors available to them as a replacement for bipolar. They had MOSFET and they had TFT. So there was a sort of battle between MOSFET and TFT. Which is going to win? Will the MOSFET win or the TFT win? Will electronics now develop using TFTs or will electronics develop using MOSFETs? And the battle was over very quickly. The MOSFET was victorious and TFT was lost out the battle. Why? Well, the reason being is, if you look at, you have to, these are central to our discussion related to flexible electronics. So if you compare the two devices, MOSFET is being made on crystalline silicon. Think about crystalline silicon means crystal, no defects, right? Absolutely no defects, and it's a pure material that is there here. MOSFET was being made on this. This is, what are you doing? You're depositing a semiconductor on glass. You're depositing a semiconductor on glass. So what happens when you deposit something on glass? Glass is amorphous. So the semiconductor that you deposit on glass also becomes amorphous. It's no longer crystalline, right? It's amorphous. It's no longer crystalline. So the material that you deposit here is amorphous. So now you have a transistor made on amorphous material versus a transistor made on crystalline material. Crystalline material has no defects. So what happens to mobility of electrons and holes on crystalline? Very high. What happens to mobility? As an example, let me tell you, mobility of electrons in crystalline silicon is? What's the number that you're carrying in your head? Mobility of electrons in silicon, crystalline silicon. Huh? 1300, 1400, let's say, yeah, 1300 or so, right? A pure silicon, 1300. If I take silicon and I deposit it on glass, right? Well, how do I deposit it on glass? Well, if I have glass substrate, I heat up silicon and using a vapor deposition method, I can deposit it on glass, okay? What do I get? I get amorphous silicon. What is the mobility of electrons in amorphous silicon? 0.5, 0.2. 0.2. Now compare, or 0.1 you will get, 0.1, 0.5 you will get through a lot of effort. with a lot of, optimizing the processing conditions and all that. You may get 0.1. So you compare 0.1 versus 1000, let's say. You're talking about 4 orders of magnitude difference in mobility. And what does mobility translate into? All performance, right? Speed, switching speeds, everything it translates into. The next is, this amorphous material is full of defects. A lot of defects, and defects will affect your reliability. So you make one transistor here, and you measure, let's say you apply gate voltage and all that, you measure drain current, and you find drain current is 1 milliampere. You make another, because it's amorphous, a lot of disorder, you'll find the current is 2 milliampere. Because of defects, this, that, the current is changing. It's not very reliable. So TFT had that problem. Performance was far inferior, and it had reliability issues. And so two things are born at the same time. One has very high mobility, 4 orders of magnitude higher mobility, made on single crystalline substrate, and very, very reliable. The other one had all these issues. And so TFT was, there was hardly a battle. People realized, well, MOS is the place. Electronics has to now take advantage of the properties of MOS, and electronics has to progress through the MOSFET route. So, but TFT had something interesting to do. So this, yes?
So you said that if we deposit silicon semiconductor on the glass, then the semiconductor will also turn into amorphous. But that will be limited to only a certain height of the silicon, because the defects cannot.
They do. You deposit 1 micron. See, the whole thing is based on thin films of material. So you deposit 1 micron of amorphous silicon, 2 micron remains amorphous. It remains amorphous. In fact, to turn amorphous silicon into crystalline, for example, what people do is they try to use a laser and they try to melt the amorphous silicon. Right? So you shine a laser on amorphous silicon and you cause a local melting. And then you allow it to recrystallize. And then you may get a small grain of silicon. So you can take amorphous silicon and use laser-based methods, and you can make a polycrystalline material. But a single crystal material, you'll never get. And the moment you use lasers and all that, it becomes more expensive methods and all that. That's it. Okay? So what happened was, TFT had, there's no way TFT could compete with the MOSFET because of the crystalline versus amorphous nature here. But TFT could do very interesting things. So this group that you see here, this is the time when I say birth of flexible electronics. So the TFT, they used materials like, they got better mobility, so they didn't use silicon, they used tellurium, cadmium selenide. Now, if you look at the structure of the TFT, the glass doesn't play any role, right? The glass is just there as a substrate. So they said, well, why do we need glass? We can make it on glass, we could make it on paper. We could make it on mylar. Mylar is like plastic. We could make it in aluminum foil. So this group, this was the leading group at where TFT was born, Westinghouse, a US company. So they made TFTs on glass, on paper, on mylar, on aluminum foil. They made multi-stage amplifiers. Once you have a transistor, you can make amplifiers, logic circuits, oscillators that could be bent, flexible, so it could be bent and all that. They could do all of these things, see? This is an early photo of a mylar sheet with all these things, nice things that are made here. TFT is on mylar by the yard, long piece of mylar, plastic, and all these amplifiers, everything made on a flexible piece of plastic here. They did all this. They did it on paper also. They did it on aluminum foil. So you could make all these nice things that are there. Flexible. Right? Flexible, can be rolled up, all those things you could do here. And so this was now, as I said, TFT was born, and I'm talking about 1967. You could do all these interesting things. So flexible electronics sort of born, I would say, with the TFT. If you want, you can say the moment TFT was born, flexible electronics was also born. Why? Because you could make TFTs on any of these other flexible substrates. You're not limited, substrate could be anything, right? You're not limited to. The other reason why I'm saying is you could make it on any substrate like paper and mylar and aluminum foil, because TFT is not based on crystalline material. TFT is based on amorphous material. See, if you want to make crystalline silicon, what do you have to do? How are these silicon wafers actually made? You have a high melt of silicon. You melt silicon and you put a seed into that and you gradually pull it out. It's a high temperature process. I can make a thin layer of silicon. I can deposit a thin layer of silicon, crystalline layer of silicon. I can do that, but I have to go to high temperatures, 800 degrees Celsius or so. But the moment I say amorphous, I don't care about crystalline nature. I can deposit these things at room temperature. The reason why I'm saying is, for example, paper cannot tolerate temperatures beyond 150 degree, paper and plastics and things like that. But with amorphous semiconductors, I can use room temperature processes. I can deposit silicon and other materials at room temperature. So that's why electronics could be done on these new materials using TFTs, because of amorphous nature of the material here. So flexible electronics was born, if you would like, with the TFT, but really in terms of amplifiers and oscillators, maybe the year 1967. They could show all these interesting things that are there here. So you have all these nice things that are there, right? A flexible amplifier. Okay, so let me ask you, a flexible rectifier, right? A flexible rectifier. Now, but who wanted a flexible rectifier? Who wants if I tell you I'll give you a flexible common emitter amplifier, common source amplifier, what do you do with it? I'll give you a flexible common source amplifier, which will work at 1 kilohertz, versus a silicon common source amplifier, which will work at 100 megahertz. Right? Which one do you want? Silicon common source amplifier working at 100 megahertz will work for 20 years, 30 years, very reliable. And then I give you a common source amplifier using a TFT made on plastic, but is flexible. You can roll it and keep it in your pocket. It will work for maybe a month, maybe, or less. And will work at 1 kilohertz. What do you do with it? Right? So it was very nice concept, very nice concept, but there were no applications. What do you do with it? So now, but note that if you look at it, this is monolithic integration. You're making now, TFT is what? TFT is made on plastic or on glass. And all the electronics amplifiers are made on plastic or glass, right? So you're talking about an IC made on plastic. IC made on plastic, IC made on whatever. Now, you see the substrate doesn't matter. What this flexible electronics is telling you is, you can make IC on anything you want. You can make IC on this piece of wood. Because what do I need to do? Let's say if this is mica, right? So if I want to make an IC on this, what do I have to do? I have to, let's say, make the surface planar, and then I'll deposit, gate, and the metals I'll deposit, and semiconductor I'll deposit. I can make a transistor on this piece of table. I can make a transistor on this piece of table, and I can make an amplifier on this piece of table. We can embed electronics on this piece of table, right? We can make it. On any substrate that you want, we could make it, in principle. What is the problem with that electronics? Performance, reliability. So all those issues were there. So it had very nice concept, but there were no takers for it. No applications. And so flexible electronics, although born in 1967, let's say, it sort of no takers, so it sort of died. The whole thing, there's this group that you see here at Westinghouse, it did all these interesting things, but couldn't do anything with it. And by 70s and all that you see here, the whole effort was abandoned, and that was the end of flexible electronics. End of flexible electronics here. But this group that had done this, they said, we have a nice device called TFT. When you invent something, it's like your baby, right? and you're in love with that baby, and you want to do something with it. So they didn't want to abandon. What can we do with TFT? They kept on saying, okay, we have a nice device. It's made, TFT, for example, made on glass, right? And MOSFET is there. Say, we can't compete with MOSFET, right? So if you have something else, we can't compete with MOSFET. It's far better in terms of that. But I have a new device. So they were saying, where can I use it where MOSFET cannot be used? So they looked around and they said, where can a TFT be used? Which application can a TFT be used where MOSFET cannot be used? Is there something like this? Okay, so this is what this group was, the group which invented TFT were looking for. Is there something where MOSFET cannot be used at all? Well, and anyway, so this is interesting to remember. Whenever something new comes in, right? Whenever something new comes in, say tomorrow you invent something, one of the first things that happens is when something new comes in, you say, well, I can use it here in known applications, in applications which are already there. For example, you look at transistor, right? When transistors were invented, how were they marketed? Look at how they are marketing the transistor. They're marketing the transistor by saying, well, look at this vacuum tube. This vacuum tube is so big and I'm so small, right? I'm so small. They're putting a vacuum tube there and putting next to it a transistor. And they'll say, look at this here. And they'll say, well, whatever you can do with a vacuum tube, I can do it much better, right? So what people who invented the transistor, what were they trying to do? Everywhere where there's a vacuum tube, replace it by a transistor, right? So that's the mentality. When you have something new, you say, well, it's better, so replace it. But this is what is very interesting here. This is by Herbert Kromer. He's a Nobel laureate for his work on semiconductors. Making a statement which is important. The principal applications of any sufficiently new and innovative technology always have been and will continue to be applications created by that technology. If you have a really new thing, a novel thing, you don't have to go and say, well, I can do what you can do, but a little better than this and all that. No, in fact, you can create entirely new applications. This is what Transistor ended up doing. Transistor ended up with a new method of manufacturing, IC. And with IC now you could do all these interesting things, all the products that you see here, which you cannot even think of with a vacuum tube. Okay? So the lesson from it is that, okay, you have a new device called TFT. Don't try and look for replacing MOSFETs and other things that are there. Look for some applications which will be enabled by that particular technology. Something which will be enabled by that, something which cannot be done. Okay? So this is what they found. So remember, this is very early. We are talking about 1960s and early maybe 1970s. So this group is sitting there and saying, what can we do with TFT? And this is what they were thinking at this particular time. See, this is where also leadership comes. People are thinking not just now what I can do. They're thinking of 10 years, 20 years ahead. So at this particular time, this particular group is saying, look at their thinking. If we ever approach solid state television, so televisions were already there, right? And televisions were what? They were also vacuum based. The CRT, cathode ray tube. They were big bulky devices that were there. So they had seen vacuum tubes being replaced by transistors. So they were thinking, will we, they're trying to project into the future. A day will come when the CRT will be replaced by a solid state TV without a vacuum tube. So they're thinking, well, what if, that what will happen? If we ever, look at the statement, if we ever approach solid state television devices, we may have to think of, a TV requires a reasonable resolution, to see images and all that. We may require these elements that you see here. A TV will have to be made up of some kind of a light emitting element. It will have to be a light emitting, and this light emitting element, let's call it LED or whatever, light emitting element, will have to be controlled, because to create an image, some will have to be on, some will have to be off. You'll need switches. So it's a solid state TV, let's say a source of light here, but you'll have to switch it on and off, and I will require switches there. And the switches will have to be transistors. And if you're talking about a large area display, even in early days, say 21-inch TV, so you will have a TV, which is a 21-inch TV, and on that TV you will have all these elements that are there, and these elements will have to be switched, right? You will need a switch. And the switches have to be fabricated on, these elements will be on glass. A large area, a display has to be glass. So these elements will have to be fabricated on glass. These switches will have to be fabricated on glass. And a switch has to be fabricated on glass. I will need a TFT. Right? Now you may be thinking, why can't I take a transistor MOSFET and solder it here? Why? Because you're talking about, look at the resolution, you're talking about 250,000 elements integrated on a small glass plate. You cannot integrate 250,000 elements because to solder it, the MOSFET will become 1 centimeter in size. And you will simply not be able to do that. The MOSFET has to be much, much smaller. And much, much smaller in size. The switch that I would like here, a switch to be connected here, the switch you can calculate, by giving a display size and all that, we can calculate how much area is allowed for a switch. The area is very, very small. So you can't do with a packaged transistor. You will have to make the switch on the glass itself. So they realize that if we ever, as you can see here, if we ever approach solid state television, this thing, we would require a TFT there. And so displays provided a unique application for large and cheap active networks, means transistor networks here. So they said, when we do reach a stage where we would make these displays, solid state displays without TFTs will not be possible. And TFTs would be absolute. And they could see that eventually CRTs would also go away and solid state TVs will come. And so they said TFT will find a place. TFT will survive. Flexible electronics, we don't know. You have to now imagine, you're talking about, you have to imagine a flexible TV and things like that. That's far ahead, right, at this particular stage. But TFT we would require here. Now, very interesting, so we'll stop now. So very interestingly, what happened was, at this particular time, there's another revolution which is occurring, which is the LCD revolution. Note that LCDs, liquid crystal displays, they have this interesting property that you apply a voltage and you can change the orientation of the crystal and make them transparent or opaque. So all those things had been discovered very early on, 1888 and all that you see, 1963. 1968 is the invention of the LCD, liquid crystal display. Liquid crystals being used for a display. And so this happened in 1968. At the same time that you're saying, TFTs are coming up. 1968 is LCD. 1970 is LCD calculator. 1971 is LCD watch. So now this opens a very interesting test. They're imagining solid state TV. Right? Solid state TV. How are you going to construct a solid state TV? How are you going to construct? You need a light source, right? Well, light source would be what? Maybe next lecture we'll go and look at it. Light source is what? An LED. LEDs had already been invented also. But LEDs require what? Crystalline semiconductors. LEDs don't work. LEDs will require gallium arsenide or some other material which is crystalline. So they require crystalline. Now, I have to make the whole thing on glass. If I take gallium arsenide and put it on glass, it becomes amorphous, doesn't emit light. So how do I make a solid state TV? Well, the route was LCD. Liquid crystal displays here. So LCD, they said, well, with LCD, you could do watches and all that. So LCD was the display element. As I said, a small element of LCD is like a capacitor. You can make it opaque or transparent by applying a voltage. And so if you have a light behind, it's opaque or small, so it becomes a light switch. So LCD became the root. So how do you make a solid state display? You make it through an LCD. If you want to make a high resolution display, you will require a switch. And so you have a TFT LCD. So that's how the TFT survived and became a major technology based on the LCD part here. Okay, so let's stop here, we'll continue.